Professor R.Fujita from RIMS, Kyoto University, will give the last of his lecture series.
Thank you. So yesterday, I finished with this R matrix. So let me recall what was R matrix. So let us take two irreducible representations in our category of finite dimensional representations of quantum affine algebra. And then, so in general, these tensor products are non-commutative, but if we deform the spectral parameters generically, then we get a unique isomorphism between differently ordered tensor products, which send highest weight vector to highest weight vector. Then this isomorphism is called R matrix, which is rationally depends on the ratio of spectral parameters. So it makes sense to consider the pole order of this R matrix at this ratio is equal to 1. Then I said that this is so this is a non-negative integer, and this is very important numerical invariant for the tensor product representations. And so at last, I stated this theorem. So this is this gives an explicit computation of this number for fundamental representations in our category C0. And this is related to the another numerical invariant, which is now for the additive category. So this is the derived category of representation of Dinkin quiver. And there is a correspondence between fundamental representation in this category C0 and indecomposable representation of this derived category of Dinkin quiver Q, which is denoted by this HQ, Happel's isomorphism. And this theorem states that this numerical invariance, R matrix invariant, is equal to the dimension of x1 of corresponding indecomposable objects in derived category. So let me explain how to prove this statement by using geometry of Nakajima quiver varieties. So this is a proof, but this is a rough proof. So first, so for in general situation, we can so R matrix is a rational function, but we can localize it. So this R matrix in this is an isomorphism between so we apply some localization and compilation at this z is equal to 1. Then it induces this isomorphism. And in terms of this localized R matrix, we can redefine our numerical invariant to be the minimal non-negative integer k, such that so for each non-negative integer, we consider this renormalized R matrix, and we consider the condition that this renormalized R matrix send this lattice of this tensor product, which is formed by the former series part. So there is no polar part here. So this is a lattice in this vector space, and this sends. So this lattice goes to this lattice. So lattice in this side. So yeah, I think this is an algebraic reformulation of the notion of polar order, right? Then let us consider the yeah. So let us consider the fundamental representations and its infinitesimal deformation. So for simplicity, I will use this abbreviation. For the formal deformation of fundamental representation. And let us write x is, so x is in this I hat. So this is a pair of Dinkin node and some integer. So let x be the pair IP and y to be this pair JS. Okay. And we divide the cases into divide the situation into two cases. So first we consider the case P is greater than or equal to S. So in this case, so by using Nakajima quiver variety, we can realize this tensor product of deformed fundamental representation as a equivalent, completed equivalent case theory of central fiber L. On the other hand, the opposite tensor product is equal to the completed equivalent case theory of M whole quiver variety. And we have a natural map from here to here arising from the inclusion. So there is a closed embedding here. So and this gives a certain homomorphism here to here. And we see that this homomorphism sends highest weight vector to highest weight vector easily. So we find that this homomorphism, geometric homomorphism, is the same as our R matrix, completed localized version of R matrix. So we found that in this case, the pole order, so there is no pole here. So this is equal to 0. And so let me note this number, d of xi. So in the derived category, we also easily find this, the x1. There's no x1. So in this case, they match it. Okay. And the non-trivial part is the other part. So let us consider the case P is less than S. And in this case, the product xy is identified with the equivalent K of M. And the product yx is the equivalent K of L. So we want to construct geometrically a homomorphism from here to here. And to do so, we use Kashwara-Kim's result. So in this case, so we take W. So this is I had graded vector space, but this is for fundamental representation. So we just take Wx plus Wy, and each component has only dimension 1. And in this case, by Kashwara's theorem, we see that the affine graded quiver variety associated with this W is actually equal to isomorphic to the representation of so X1 quiver. So this is X1 quiver we discussed yesterday. In particular, in this case, this affine graded quiver variety is just an affine space of dimension dxy. And so I denote this affine space by E. Then we can regard this equivalent K to be a equivalent K of this kind of fiber product. And on the other hand, we have we can identify this to be this fiber product, because this is central fiber. So this 0 is the origin of this vector space. MW is certain smooth variety which has a proper map to this affine space. But we do not use the concrete description of M. We only need to know what is this M0. And we can construct a homomorphism from here to here by using convolution. So we have a convolution from K, equivalent K of this fiber product times equivalent K of this fiber product to equivalent K of this fiber product. So note that this space is just a point. So this is just equivalent K of point. And the generator of this equivalent K is given by the structure sheaf of 0. This is just a skyscraper. Yeah, in E. So we consider the convolution with this of 0 in equivalent K of this fiber product to get the homomorphism. So this gives a homomorphism here. And we see that, so here we have highest weight vector. And this is actually given by O of 0. So this means that, so we consider the MW. So this is a disjoint union of MVW for various V. But the highest weight vector comes from the component of so the zeroth component. So we take V to 0 to be 0. Then this is just a single point. So this is just 0. And we consider the convolution of them. And but from definition, we can easily see that this is a convolution. This is given by tensor product. And this tensor product should be taken on the ambient space. So ambient space in this case is this E. So we first take the resolution of this scraper sieve in this affine space of dimension dxy and take tensor product. And by using so-called Koszul resolution, so we take Koszul resolution. So we have a resolution of this O of 0 by so we have this resolution. So given by the wedge of E star times O of E. So K. So there's a Koszul resolution. So from this Koszul resolution, we see that in the equivalent case theory, this O of 0 is equal to the alternating sum of this representation times this OE. And this is equal to, in our terminology, this is equal to 1 minus Z2 over Z1 of dxy of OE. Right? So if we replace this one of them, for example, this right factor by this class, then we get this is just 1 minus Z2 over Z1 of dxy of O0. So in particular, this homomorphism sends highest weight vector to the 1 minus D2 over D1 dxy times highest weight vector. So this tells us that this homomorphism should be identified with 1 minus D2 D1 dxy of R matrix. So this commute. So, and from this reformulation of this number O, so from this observation, so we finally get that O of B1, B2 should be, so this is minimum number such that it sends this lattice to this lattice. So this is at least smaller than or equal to this dxy. So this is half of the proof. And for the opposite inequality, we use another technique, some pervasive theory, but I omit because I've never explained this pervasives in my talk, so I omit. But there is a way to see this opposite inequality. So basically, this is the reason why we get to this equality from geometric information. Yeah, okay. And in the remaining time, I'd like to explain the application of this kind of fact. But before that, is there any questions so far? Yes? Oh, so sorry, I do not understand. Yes. Ah, I see. So actually, this dxy is easy to compute. This is easy to compute. Yeah, basically because x to k for indecomposable representations. So this is usual X4 quiver representations. And this is easy to compute by using Weyl group combinatorics, actually. And in the derivative category, we only just have shifts. So essentially, this is Weyl group combinatorics, right-hand side. But on the other hand, this number, 4 over R matrix is quite difficult to compute. It is very difficult. Yeah, but in this case, G is actually equal to maximal torus because these just in this case they have different degrees. So G is equal to C star acting here, C star acting here. So this is equal to T torus. Thank you. And so let me now try to explain the application, which is about to generalized Schur-Weyl duality. So the classical Schur-Weyl duality was the following. So we consider that real algebra SLN C and consider its fundamental representation, the usual vector representation. And we can consider the tensor power of this representation. Then, because this is a representation of real algebra, there is an action of symmetric group which permutes tensor factors simply. And these two actions are commuting each other. So this here is a bimodule. So this is classical Schur-Weyl duality. And this actually yields an monoidal functor between the module categories. So if we have this kind of bimodule, so we have a functor from category of modules of a symmetric group, white group algebra, to the category of modules of a real algebra, just given just by tensoring this bimodule over the group algebra. So this is a functor, and if we take direct sum over m, yeah, maybe from 1, then we get yeah, maybe from 0 this functor, and this is a monoidal category because we can consider the tensor product of real algebra representations, and here we have some monoidal structure given by parabolic inductions. So if we have m modules over Cm, maybe m1, then we can consider its tensor product with another module, Cm2 module. Then we index up to modules of a symmetric group of degree m1 plus m2. So this is tensor product over this C of Young subgroup. So there is a natural embedding of this direct product of group inside this group of degree m1 plus m2. So we consider the tensor over this. Then this here is a so tensor product. So here we have monoidal structure, and here we have monoidal structure, and this functor, where is T? Same tensor D. Sorry, this is M. Sorry, this is a mistake. Thank you very much. And this is a monoidal function. This gives a nice monoidal functor. And there are many variants of this kind of construction. And in this talk, I'd like to focus on quantum affinization of this construction. Namely, we replace real algebra with quantum affine algebra. And as a replacement of this symmetric group, we can take so-called affine Hecke algebra associated with GLM. So this is affine Hecke algebra. Yeah. Then this representation can be should be also replaced with this loop version of fundamental representation, and its tensor. And the action here is now given by R matrix. So this is the something called the quantum affine Schur-Weyl duality. But generalized Schur-Weyl duality is yet another generalization of this. So we want to further generalize this quantum affine algebra to general type. So G is general simply algebra, and we would like to generalize this affine Hecke algebra. But in this case, the counterpart is not an affine Hecke algebra of other reductive group, but in this case, we have to take certain algebra called the quiver Hecke algebra. So this is a kind of generalization of this affine Hecke algebra of type A, GLM. Then we can also construct the bimodule, certain bimodule, and this gives a nice functor between module categories. And this kind of generalization, so it is this kind of generalization which I'm going to talk and this is constructed by Kang and Kashiwara and Kim recently. And I will explain what is this more precisely.
The question about your generalization is in one category, in the sense of one category.
Yeah, in one category. I only consider one category. Yeah. So first, I explain what is this quiver Hecke algebra. This algebra is also known as Hobanov-Lauder-Ruquier algebra because they introduced it, Lauder and Ruquier. So they introduced this algebra independently, and this is attached to a quiver without loops. And the vertex set, I will denote this vertex set of this quiver to J. So vertex set. And attached to this quiver, we can consider the corresponding symmetric Katsumudi algebra. So this is the Katsumudi algebra whose Dinkin diagram is the underlying graph of this quiver. And we consider its set of simple roots and consider the positive cone. Positive cone of positive cone generated by simple roots. And for each beta from this sum of simple roots of this symmetric Kac-Moody algebra, we can attach this quiver-Hecke algebra. So let me explain. And to each beta, first we prepared the set of sequences of indices such that the corresponding sum of simple root is equal to beta. So here M is the sum of Bj. Okay, so this is a finite set, and we have an action of symmetric group Sm by permutation, by place permutation. So this is a setup. So I do not give a definition of quiver-Hecke algebra, but so we take F ground field, and we assume that characteristic of F is equal to 0, and so H2 of beta is an F algebra. Yes, F algebra generated by, so this is presented by generators and relations. So, and the generators are three kinds. So we have U generators and tau generators and E nu from this set of sequences. And there is some explicit relations. So sorry, this is F algebra. Maybe I like this way. F algebra generated. And I will lay some of relations. So first, this E nu, they are orthogonal idempotent. And if we sum up them, then we get 1. So yeah. And the UI commutes with this idempotence. And UI and UJ are commutes with each other. So in particular, this quiver-Hecke algebra actually. So we consider the sub-algebra generated by U and E. Then it gives a direct sum of polynomial rings. So it gives something like this. Yes. So this is definition, and this algebra actually sits inside our quiver-Hecke algebra. And these tau elements are something called braid elements. So So to define affine Hecke algebra, we also have braid elements which satisfy braid relations and Hecke relations. And this is some counterpart of that braid element, but not precise. And there are several relations involving these braid elements, but I would not like to write it down because it is a little bit lengthy. So instead, I'd give a so there are some other relations, but instead I would present some faithful representation of this quiver Hecke algebra. Actually, we can embed this quiver Hecke algebra inside the algebra of endomorphisms, linear endomorphisms over this sum of polynomial rings, actually. So there is an algebra homomorphism. And under this homomorphism, tau, so the UI and these idempotents goes to just multiplication here. And tau goes to the following element. So let us pick an orbital element from here. Then tau k acts on this element by the following rule. So there are two cases. First case is the case nu k is equal to nu k plus 1. And in this case, this acts as a de Majeur operator. So this is something like this. So let me, I read this one, sorry. So this given by this RKF u minus fu RK minus RK plus 1 times nu of G, right? So this is the first case. For the other case, otherwise, sorry, this RK is a permutation of UK and UK plus 1. So this is just a transposition of UK and UK. Then this fraction, so this denominator cancels. So it is a polynomial. So anyway, we get. And for the other case, we consider this UK plus 1 minus UK times M and RK of F U. And this idempotent is twisted by transposition. So here SK is a simple transposition of this symmetric group which acts on this set of sequences. And M here, sorry, M here is where M is the number of arrows from mu k to mu k plus 1 in our fixed quiver Q. Okay. So this gives a faithful representation of our quiver Hecke algebra. But anyway, so this is the definition. And there's one more thing. So this quiver Hecke algebra actually a graded algebra. So this has a Z grading given by so degree of idempotence should be 1, and degree of UI is equal to 2, and element tau also has some degree, but we can read off we can read off their degree by this formula. So we omit them. But anyway, so it has a grading. So we can consider the category of category of graded modules, and we restrict to the finite dimensional graded modules, and consider the direct sum over or beta from Q plus, the positive cone. Then this category, so this will be denoted by simply HQG mode. So this category actually is this is an abelian monoidal category. And this monoidal structure is given by an analog of parabolic induction. I omit the detail, but there is a corresponding construction. Excuse me. So P beta is infinite dimensional graded module over this quiver Hecke algebra. So P beta itself is not belonging to this category of G mod. It is infinite dimensional module. But here we only consider finite dimensional module. Then this quiver Hecke algebra is very nice algebra in the sense that this categorifies the quantum group. So this is the fundamental theorem due to Hobanov-Lauder and Riquier. So they prove that if we consider the Grothendieck ring of this category, monoidal category, then this is isomorphic to the half of quantum group associated to the symmetric Kac-Moody algebra GQ. But here we take we have to take its dual. So this is dual integral form, so-called dual integral form. So this is integral form. So in particular, this is a module over this ring of Laurent polynomials in quantum parameter Q. And this action of Q, we have the corresponding action of Q, and this is given by the grading shift. Grading shift. So because we are considering graded modules, there's a grading shift factor acting here, and this corresponds to the action of quantum parameter here, this side. And furthermore, Riquier and Bagno-Vassereau prove that so here we have a canonical basis consisting of simple representations. Then they identified this basis with the so-called dual canonical basis. In the sense of Lustig, or upper global basis. In the sense of Kashiwara. But anyway, in this sense, quiver-Hecke algebra gives a categorification of quantum groups. So now I'm ready to explain what is generalized quantum affine Schur-Weyl duality. Generalized Schur-Weyl duality. Due to Kang Kashiwara Kim, I will explain. So this is very, how to say, general construction. Actually, given any family of, given any collection of real representations, real simples in category C. Category C is the finite dimensional module of a quantum affine algebra. So we start with this quantum affine algebra side now. And let us assume that we are given a collection, any collection of real simple modules. Then from this family, we construct a quiver Q, which is obtained from this given collection. Sorry, this is UQ G hat finite dimensional modules. See in this case, and this construction work well for G of general type. So in this talk, I considered so far I have only considered type ADE because I wanted to apply geometric technique, but here this construction of general Schur-Weyl duality we can work with any type, including of course the BCFG type and also twisted type, and maybe with quantum affine superalgebra. So yeah, but anyway, so we construct a quiver defined by, so we define a quiver whose vertex set is given by this index set J, and the set of arrows are given by the following rule. So the number of I to J in this quiver is equal to the whole order of R matrix between Vi and Vj. So by this rule, we can construct a quiver, and associated to this, we have the corresponding quiver Hecke algebra. Okay, so this quiver Hecke algebra is now depending on this choice of collection of simple representations. And we construct a bimodule between quantum affine algebra and this quiver Hecke algebra. So which is denoted by yes, Bj tensor beta hat. So I will define this thing. So this is a sum over nu running this set of sequences, and we consider for each nu the corresponding tensor product of representations. But now we take its deformed version. So Bj hat is defined to be the Bj deformed by so something like this. So and on this space, so we give an action of quiver Hecke algebra. So by the following rule, so this action is given by, so we need to determine the action of each generator of this quiver Hecke algebra. Yeah, and E nu is E nu action is just given by the projection to a new component, and UI action is equal to the Z I minus 1 multiplication of this formal spectral parameter. So this acts on this V of mu k VQ. So this is mu at. So this is multiplication of spectral parameter, and the tau action is given by actually this formula. So I described here the polynomial representation. So we have the action of tau on this polynomial representation, and we here consider the same formula, but we replace this RK here, here and also here, by the corresponding R matrix, R matrices. Then we get an action of quiver Hecke algebra, and actually this action can be extended to the action of a completion of quiver Hecke algebra. So this is completion. Then by the construction, this action commutes with the action of quantum loop algebra, or quantum affine algebra. Anyway, then therefore this gives a bimodule. So by this construction, we get a monoidal functor. So this is a theorem due to Kang Kashiwara Kim. So we consider the category. So now we consider the completion of quiver Hecke algebra. So there is no longer grading. So we just consider the finite dimensional module over this completion. But anyway, this is if we consider the sum of this modular categories over beta, then we get monoidal category, monoidal abelian category, and we have a functor from here to the category C of finite dimensional modules over quantum affine algebra just by tensoring. So we consider for each beta we consider the bimodule and consider tensoring. Tensoring over quiver Hecke algebra. So this functor is by F depending on this Vj. Yeah. Then we can say that this is a monoidal functor. Yes, this is the generalized quantum affine Schur-Weyl duality functor. And so at first sight, it is a little bit, sorry, I forgot to mention one important thing here. So here the construction involves this pole order of R matrix. So this is because this is to make sure that this, so this operation here, replacing this small r with R matrix is well defined on that tensor product. Yes, because of this, because multiplying this factor, we can cancel out the denominator of the corresponding R matrix. So it gives a very defined operation, very defined homomorphism on that product of completed modules. Yeah. And finally, I'd like to explain how to understand this construction by using graded quiver variety. So we give a geometric interpretation for some special cases, but so now we assume that G is of type AD. And further assume that our collection of real simple modules consists of the fundamental representations. So Bj is equal to pi of xj. So we assume that there exists an embedding from j to I hat, so which divides this collection. So we only consider these restricted cases, but in this case we have geometric interpretation of this functor. And from this data, we have to define this quiver. And this is given by, so the vertex set is equal to j. Or, yeah, and yeah. And sorry, Q1 is given by this pole order of our matrix. And we see that this pole order is equal to actually the dimension of x1 of corresponding indecomposable object in a dentin quiver. So this is given by d of xi xj. Yes. So this quiver actually is equal to the gamma restricted to image of j. So gamma is x1 quiver. So the number of arrows in x2, this gamma is given by this d. So by definition, we have this identification. This is the consequence of the theorem, which I presented at first. So for simplicity, I denote this by gamma of j. So this is our quiver, and we consider the corresponding quiver Hecke algebra. So H of gamma j we consider. So by the construction due to Kang Kashiwara Kim, we have under this setting a bimodule between this quantum loop, quantum affine algebra, and quiver Hecke algebra attached to this quiver gamma j. Yeah, completed. Yes, and we identify this with certain geometric objects. So we consider the so recall that we have a homomorphism due to Nakajima. Which from quantum affine algebra to the convolution algebra of corresponding quiver variety. And actually, quiver Hecke algebra has a geometric realization by using convolution algebra. This is due to Baraniol-Basselot. Which so they proved that theorem, so which says that the irreducible representation corresponds to the right-hand basis by using this kind of geometric construction. But anyway, so we have geometric interpretation of quiver-Hecke algebra. Now this is given by so-called a kind of flag variety. Yeah. So here I do not explain in detail, but E is a space of representations of gamma with fixed graded vector space W. And there is a proper map from here to proper map from the certain analog of flag variety. So this is a kind of maybe we can say that this is a quiver analog of flag variety. And we have some proper map here. Okay. And on the other hand, so we have Nakajima's quiver variety here to here. And recall that the Taylor-Shirotsky theorem, which said that this affine graded quiver variety is embedded into the space of representation of representation of X1 quiver. So actually, this variety is embedded into this E. Okay, so this is Taylor-Shirotsky. So by using this, so we may replace M0 by this E, and we want to construct intermediate things. So we consider the equivalent K of M, fiber product M and flag. So this makes sense. And by convolution, we have we can make this as a bimodule, and we can actually identify this bimodule with this Kang Kashiwara Kim isomorphism. So by using the tensor product theorem. Yeah, basically applying this tensor product theorem, we can identify this and this. Yeah, here we need to use some non-trivial thing, but we can do this. So this here is a geometric interpretation of this bimodule, and the functor like this. Yeah, I have to finish. Yeah, but I just mentioned the special case. So there is one very nice special case. Case of this construction when J is equal to I, and this X is given by the position of simple representation in the Australian quiver of derived category. So let us consider that this case. Then our quiver gamma J or gamma I is actually identified with Bintin quiver Q. Of type G. So in this case, we have a functor from HQ module. So this is quiver-Hecke algebra of, so this is same type as G. So this is ADE finite type quiver-Hecke algebra. And from here to here, we have a functor. So this is category C0 for quantum affine algebra module. And we can prove that in this special case, this functor is a free faithful embedding. And the irreducible representation here, so in particular, irreducible representation goes to certain irreducible representations in. So this embed, yeah, to here. So in particular, so the image of this functor categorifies the half of quantum group, because this category also gives that, sorry, but the category for quantum groups, but the quantum group specializes at Q1 because we do not have grading in this setting. But anyway, this image of functor, this categorifies the quantum group, dual form of quantum group specialized at 1. So this is identified with the maximal unipotent subgroup. Group of G, and here G is the Lie group corresponding to our fixed type ADG. So yes, I think this is a very special case, but this construction of Kang Kashiwara Kim is very general, and so we can construct the functor not necessarily fundamental modules, or we can work with non-simple rest type or twisted type or quantum affine superalgebras. And for that case, we do not have any geometric interpretation like this so far, but I expect that there will be something for outside type ADE fundamental modules. Okay, I stop here. Thank you very much for your attention.